Hi everyone, I'm Mr. K. Welcome back to Everything's Relative. And today we're going to be looking at another crash course for Cambridge A-Level Physics, and it's on the topic of gravitational fields. Now, this is one of the first topics you'll encounter when you move over to the second year of your A-Level Physics diploma. It's the first time you'll actually be introduced to fields, if you're doing the more modern syllabus at least. So before we talk about what a gravitational field is, I think we first need to discuss what a field is. So, what is a field? You may or may not have experience with fields, or you may have heard the word field. You may have a vague idea. But let's first define a field. Now, imagine, well, you don't have to imagine. I'm sure all of you are watching this video while on Earth, and you are seated, most likely, or standing if you wish, but you are firmly rooted to the ground. And that's because you feel the Earth's gravitational force. There's a force between you and the Earth, which keeps you on the ground. And any region in which an object experiences a force is a field. So if I write this down, a field is a region in space, but I'm too lazy to write that, in a region in which an object, could be any object, experiences a force, and similarly could be any force. Now, the force I was talking about was a gravitational force, which means that the field that you are in, or you are in, is a gravitational field. So let's define a gravitational field. It's not that important, so it doesn't have to be that big. What is a gravitational field? So just like a field, a gravitational field is a field, but it's more specific. So it is a region in space in which a gravitational force is experienced. So is a region in space in which, now it's not just any object that will feel a gravitational force. It's only objects that have mass. You know that only massive objects can feel a gravitational force. So we replace object with mass, in which a mass or massive object experiences and we can be specific about the type of force as well, experiences a gravitational force. So a gravitational field is a region in space in which a mass experiences a gravitational force. So if we have a massless object, it's not going to feel a gravitational force. It doesn't mean that there isn't a gravitational field. It just means that if we still take a mass and place it into that region, it will feel a force. So if a mass experiences a gravitational force, it is in a gravitational field. So any region, any area in space. Normally we think of forces only acting at a point, but we know that anywhere we go on the Earth will still pull us towards its center. And so the entire area surrounding the Earth is the Earth's gravitational field. Now, what do we know about the gravitational force? Well, some of the things that we should know is that it's the weakest force. And we'll see why we discuss it to be the weakest force of the four fundamental forces. But basically, the gravitational force is hugely powerful if the scale is very large. So the Earth is massive in size, which is why we notice the Earth's attraction between us, or the attraction of us towards its center. But on a small scale, if I had two objects, if I placed two books on a table, we wouldn't notice any attraction between these two objects. And that's because the mass of each of these objects is not large enough. And so that's why we say the gravitational force is a weak one. It does work dramatically, but only on a large scale. And we are only going to consider large objects. Now, you're going to see a contradiction with some of the equations, but we're going to assume that the only thing of relevance in gravitational fields are large objects. So the first place to start is on the gravitational field strength. So as you can probably tell, that tells us the strength of the gravitational field, how strong a gravitational field is. So we call this, it's a new quantity. basically relearning. Gravitational field strength. So this new quantity, and we won't give it a symbol just yet, we'll call it gravitational field strength. It is defined, now we need to define this gravitational field strength. It is defined as the force that a mass feels when it's in a gravitational field divided by the mass of that object, force per unit mass. We give it the symbol small or lowercase g, and we can write this as g is F over m. This looks familiar. This looks like F is equal to ma, which it is. It is a special form of Newton's second law. It can be found from Newton's second law, which also tells us that the relationship between weight and mass on Earth, W is equal to mg, which we know from AS physics. Now on Earth, we know this value g to be 9.81 meters per square second. So this applies only near the Earth's surface. So we'll talk a bit later on why this is constant near the Earth's surface. But if we look at the equation, it's a force per unit mass. So surely it should have a different unit of measurement. And yes, I do. The equivalent of meters per square second is Newton per kg. So a field strength, which gives us a Newton, which is measured in newtons per kg, can also be measured in meters per square second. So it also gives us the acceleration of free fall as you approach that object. And this large object in this case is the Earth. So this is the gravitational field strength, and we'll derive another equation for the gravitational field strength later on. But this is how we define it. It is the force per unit mass acting on a point mass, or acting on a mass at that point in space. Now, how do we represent gravitational field strength? Well, we can represent them visually using field lines. Again, for many of you, this is probably the first time that you will see what a field line looks like. Again, you may have an idea, but now we're going to go into a bit more detail. Now, what is a field line? A field line is a line. I draw a line, and that line represents the field. What that line does, and we'll draw some now, firstly, and most importantly, gives us the direction of the field, which gives us the direction of the force. Now, the good thing about gravitational fields is that the gravitational force is always attractive. So the direction of the force on a point mass. Secondly, what purpose do field lines serve? Well, they also never cross, because that would be ambiguous. You would have, if two field lines were to cross, then the force on a particle will be in two directions at the same time. One force can never be two forces, so they should never cross or overlap. So field lines should always be separated. And what we can also tell from the field lines is that their closeness, how close two consecutive field lines are, tells us the strength of the field. So I'm sure whichever textbook you're using, this is mentioned there. So closeness indicates strength. So let's draw some field lines. Now let's assume this is somewhere on Earth, and I have some field lines. I'm going to place them next to each other such that the spacing between them is constant. Or well, at least as my eye can tell me it's constant. So these are field lines. Now it's a line with an arrow like a vector, and the direction is downward. So what this tells me is that the gravitational field is pointing downward. Now remember, for the Earth, the field lines are radial, but the Earth is large, and so we can assume that on any local area of the Earth's surface, the field lines are uniform. This is a uniform field. So look at the spacing between consecutive field lines. They are constant. So what does this mean? This means that the field strength is constant. So anywhere in this gravitational field, I'll have the same value for G, like it is anywhere on the Earth. And so if I place a mass, let's change the color of this mass. Let's take any object, tennis ball, for example, and I move this object anywhere in the field, it's going to feel the same force because the field strength is the same. And so this is constant field strength, or a uniform field. Uniform means the same throughout. So the Earth's gravitational field is assumed to be uniform near the Earth's surface. Now let's change it up slightly. So here the force felt by the tennis ball, or the mass, is constant. Let's change it up slightly, and let's make the field lines not be parallel anymore. Now notice again, these field lines don't cross, and for our first example, the closeness indicates strength. Since the closeness between consecutive field lines is the same everywhere, the strength is constant. But here, that distance and that distance are not the same. And so the field strength is changing. So the further apart the field lines are, I didn't mention this, the further apart the field lines are, the lower the field strength. Now this makes sense for a massive object like the Earth. The closer you get to the surface of the Earth, the stronger the gravitational field, which is why satellites can move without falling to Earth, since the gravitational field strength is slightly weaker in space. And this field is changing. So the field strength is changing. This is not a uniform field. So the field gets stronger as you get further and further down. And so the force felt on an object is not constant. So if I take my tennis ball again and place it in here, it's going to feel a smaller force when it's higher up, and then the force will increase as it gets closer towards the source of the field. Remember, the arrows in this case are pointing towards, well, the massive object, because gravitational forces are always attractive. So what types of fields do we have? Well, we have a uniform field, and we have one that points inward. So let's take a point mass. Let's assume there's an object where all of the mass is concentrated at a point. Then the field lines, so this is some massive object. When I say massive, I simply mean something that has mass. I don't mean massive in the sense that it's necessarily very large. So what I know is that the field lines will all point inward because the gravitational field is attractive. So there's a field that exists around this massive object, a star, the Earth, the planet, whatever. This mass we can refer to as a point mass, and the field lines are inward, and the shape of the field lines pointing in towards a point we call radial. So this is a radial pattern. So these are inward radial field lines. What happens if I assume that the object's a sphere, like the Earth? Well, it's the same. Whether you are in Alaska, whether you are in Australia, the field lines, the gravitational field always pulls you towards the surface or the center of the Earth. And so the field lines must be radial as well, radially inward. So the field lines are identical. So it's not a point mass anymore, but now it's a sphere with the mass evenly distributed. And what do I get? I get inward radial field lines again. So what does this mean? Now, most objects in the universe that are significant in size, that are gravitationally significant, are roughly spherical and roughly have their masses evenly distributed. So for simplicity, we're going to assume that all spherical objects that have their masses evenly, uniformly distributed can be imagined as point masses, where the point in question is at the center of that sphere, the center of mass, if you would. And this makes our calculations and our mathematics a lot easier. It's not always the case, but it's often the case, which makes a lot of the mechanics a lot easier. So let's now talk about this gravitational force. And let's put some mathematics to all of the concepts. So let's talk about the I always have a problem spelling this word, gravitation. I think it's right. Gravitational force between point masses. So you can see we're immediately going to deal with point masses. Okay, so a point mass is a point in space in which all the mass of the object is concentrated. Now, what did Newton see? So Uncle Newton, I can call him that. Uncle Newton said that if we have two masses somewhere in space, m1 and m2, now we assume there's no other forces acting on these masses, but they will attract each other. If the separation between these masses is r, the distance, these are point masses, so if the separation between the center of these two spheres is r, then m1 feels a force of gravity to the right, as we've drawn it, and m2 feels a force to the left. The force is equal in magnitude and opposite in direction, thanks to the same Uncle Newton's third law. And he found something very interesting. So from his third law, we know that the force on m1 is equal in magnitude and opposite direction to the force on m2. So I'll just make that clear, it's opposite in direction. Now, if we're only concerned about the magnitude of the force, which we are for now, then Newton said that the force is proportional to the product of the masses, m1 times m2. This is a hugely important result. He also said that the force is inversely proportional to the square of the separation between the objects, between the point masses. So the larger the masses, the greater the attractive force, and the larger the distance, the weaker the attractive force. So the attractive force drops exponentially with distance. So a graph of F against R will decrease quite rapidly as we go further from the massive object. The gravitational force weakens quickly. So if we put these two together, we get that F is proportional to m1 m2 over r squared. I need to turn a proportionality into an equation, which means I have to add a constant of proportionality, which in this case Newton found to be g m1 m2 over r squared. So g is the universal gravitational constant, or simply the gravitational constant. Now, do not mistake this for lowercase g. Lowercase g is 9.81 near the Earth's surface, and that's it. Uppercase g is constant anywhere in the universe. And uppercase g is 6.67 times 10 to the minus 11. Now you can do some dimensional analysis, but the units of g is Newton meter squared per kg squared. Again, not difficult to find if you rearrange this equation. So this is the gravitational force between any 2 point masses. So if I have two masses then the formula is quite straightforward. The greater the masses, the greater the force. The greater the distance, the lower the force. So this tells us, basically, describes to us how things in the universe attract each other and how objects can exist in space close to one another as they do. And specifically, we want to talk about stars and planets, at least for now. And what we know is that most stars and planets have a circular orbit going on. So we need to talk about circular orbits, but also about our other uncle, Kepler, but specifically Kepler's third law of planetary motion. So now we know there's an attraction between 2-point masses. So what I need to do is I need to take a star and a planet, which I already have. So I'm biased since most of us should live on Earth. I'm going to use the Sun as the star and the Earth as the planet. Now, we all know that the Earth's orbit around the Sun is not actually circular, but we can assume it to be circular, roughly circular. And so if we assume that the orbit of the Earth is circular around the Sun, my circle is not very circular, but does the job. So what we know is that gravitationally significant objects like the Earth will orbit other gravitationally significant objects like the Sun. So I'm going to be more general and say star and planet, but we can think of it as the Earth and the Sun. So if the Sun has a mass uppercase m and the planet or the Earth has a mass lowercase m, then Newton's law of gravitation, by the way, I don't know if I've mentioned this, but this is Newton's law of gravitation. Actually, Newton's law of universal gravitation, which is true, well, he thought to be true throughout the universe. So any two masses will attract each other with a force that is proportional to the product of the masses and inversely proportional to the square of the separation between their centers. If ever you're asked to define or state the law, that's how you would state the law. Proportional to the product of masses and inversely proportional to the square of the separation between their centers. So now I have the center of the star. If I assume the planet and the star to be point masses, then the points are located at their centers, separated by a distance r. Now what we know is that the Earth is whizzing along. It's whizzing along with some speed v. It also is rotating about the star. It's rotating in this sense, in a clockwise direction. Now, if an object is moving at some speed v, but it's orbiting something at the center, then there must be a force causing centripetal motion. And guess what? It's in this case, the only thing that can be causing the centripetal motion, the only thing responsible for the centripetal force is the gravitational force. There isn't any other forces that are significant enough to cause this motion. So we have centripetal motion for our planet orbiting its star, and the period of this motion is t. Since there are no other forces acting on the object, then the gravitational force must equal the centripetal force. If we go back to Newton's equation, we can now equate these two and we can determine another equation. Now let's look at the star as the object that doesn't really move. The star is quite massive. The sun is much more massive than the Earth, and so it will do very little moving, whereas the Earth does more of the moving, more of the orbiting. So if the Earth is the orbiting object, then the force between them is gmm over r squared, the gravitational force. And we know from circular motion that this is little m v squared over r. Okay, so we can equate these two equations, and immediately we can see, when we equate these expressions, that some terms will cancel. But also, the period of the Earth's orbit around the Sun, one complete orbit, is 365-ish days. But we know that the speed at which the linear speed v, the tangential speed v, at which the Earth is traveling, speed is distance over time. So distance divided by time. The distance for one complete orbit of the Earth is 2 pi r, the circumference of its orbit. The time is its period, t, so that's 2 pi r over t. This means that if we do a little bit of mathematic, we get t squared, I'm not going to do this, it's fairly straightforward, is 4 pi squared r cubed divided by g uppercase m. So we went from here to here, like I said, with some mathemagic. So why is this equation important? It's important because if I know the period of orbit of a planet around its star, I can tell how far from the star rather the planet is. I can calculate r, provided I know its mass. But if I know the period and I know the distance, which are things that we can measure, we can tell the mass of that object. So without any direct measurement of the mass, we can tell the mass of celestial bodies. So this is quite a significant equation. And this law is Kepler's third law, and now I'll give it its full name, Kepler's third law of planetary motion. Not plant motion. This is not biology. Planetary motion. So we're not really concerned with Kepler's other laws, but just the third law, because it's fairly easy to derive. And it's something you should know how to derive. So complete the relevant mathematics to complete the derivation and understand the derivation, because it could be asked of you that you need to derive that equation. Now let's turn our attention to something a bit smaller. Rather than a planet orbiting a star, we're going to look at satellites. There's a little bit that we need to know about satellites. I'm not going to go into too much detail, just cover what's relevant. So now what I'm going to do is I'm going to replace, we don't need the sun anymore, the sun doesn't exist. We're going to take the Earth and make the Earth bigger than our satellite, as it should be. So I have the Earth and I have a satellite. When I say satellite, I'm talking about a man-made satellite in this case. Remember, the moon is also a satellite, but the moon is a natural satellite. Now, what we do know is that satellites, mostly used in communication, orbit the Earth, and the path is also roughly circular. And the way we get them to not crash into one another is to put them into different orbits of different heights. Now, what I know for certain about the Earth is that the Earth is rotating. It does a full rotation in 24 hours. So as the Earth rotates, remember one thing, I want my satellite to stay directly above where I am at all times. I want a signal to be sent from wherever I am on Earth to the satellite for communication purposes, and then back to some other point on the surface of the Earth. Now, if the Earth rotates, let's try something fancy. If the Earth rotates, then I can no longer send a signal because the satellite is no longer directly above me. The satellite is now at a different point relative to me. And so if the Earth continues to rotate, I have to wait a full day before the satellite is directly above me in the position that I want it to be. So that's quite annoying. So what we do to overcome this is we make our satellite revolve around the Earth with the same period. T is 24 hours. So what this means is if I ever look up into the sky, I will always see the satellite directly above me. The satellite was moving in the other direction, still wouldn't help me. It'll just be running away from me. I wouldn't be able to send my signal straight up into space. And so if I keep the satellite in this way, then as I rotate the Earth, then so too does my satellite rotate. And so that orbit is called a geostationary orbit because relative to Earth, relative to us looking up, the satellite is always stationary. And so this, obviously there's more to be read about this, but this is called a geostationary orbit. And you can do some derivations of the equations, try to figure out the ideal orbit, ideal altitude for a satellite, etc. But basically, this is a geostationary orbit. Okay, so that's talking about satellites and satellite being a planet around a star or a man-made satellite around the Earth. So now, what happens if I have a point mass somewhere in space and I want to know the field because of this point mass? Even if there's nothing around, feel the field. So the gravitational field of a point mass. So let's say we have our mass that we are interested in. We'll call it uppercase M, somewhere in space. We know that the field lines around this point mass are radial, like we said before. These are radial field lines. They all point inward towards the point mass. And let's say we have another mass, a test mass. We'll call it little m, somewhere else in space. And it's going to be attracted towards our mass. And again, we'll call the separation between these masses r. Now, this field strength, G, around our mass, we said is F over m. Force felt by our test mass divided by the mass of the test mass. Well, this is 1 over m, and now we have an equation for the force from Newton's law, G big M little m over r squared. So guess what? We are left with G big M over r squared. What is this equation? This is the field strength of a single point mass. So if I want to know the strength of a point, the strength of the field due to a point mass at a distance r, this is the equation, gm over r squared. If I make m larger, if I make it heavier, if capital M, uppercase M increases, the field strength around this mass gets greater. If I increase the distance from the object, then the field strength gets slower. This makes sense. We all aren't attracted to the gravitational field of stars in the Andromeda galaxy because their distance is so far away, they're almost at infinity. So their gravitational field strength is not high close to us. Obviously, as you get closer to those stars, the gravitational field strength increases. And so that's the field due to a singular point mass. Now, this G, it's very difficult to see how this G can give us 9.81 and where that 9.81 comes from. So let's specifically talk about the acceleration due to free fall, which is what we call it on Earth, or near the Earth's surface. So the acceleration of free fall, which we also give the symbol little g, and why is this acceleration constant? So if I do a physics problem and I throw a ball up into the air, I say g is constant is 9.81. But if I'm throwing a ball up into the air, then surely little r is changing because the ball is moving through the gravitational field further from the center of the Earth. So what we'll do is just a basic understanding, conceptual understanding. So let me take my Earth again. So I'll take my Earth and I'm going to use a random tiny object, maybe a few kilometers in space. So it's still close enough that it will feel a significant force, but not necessarily on the surface of the Earth. So what I have here is that the radius of the Earth, whatever that value is, I'm going to call uppercase R. And then the altitude or the height above the surface of the Earth of the object, whatever it may be, we'll call lowercase r. Now this object feels a force F pulling it towards the center of the Earth. It has a mass little m and the Earth has a mass uppercase M. What we know is that its altitude, whatever its height may be, is insignificant as compared to the radius of the Earth for objects close to the Earth's surface. We also know that its mass for everyday objects, if it's a tennis ball, even if it's a satellite or a rocket, is insignificant as compared to the Earth's mass. So the field strength G is the force divided by the mass of the object, which is Gm over r squared from that equation. But r in this case is uppercase R, the distance between the center of the Earth and the center of our object is uppercase R plus lowercase r, and we square that. But wait, we said that uppercase R and lowercase r are quite different. So what this means is that this is approximately Gm over uppercase R squared. And that's because uppercase R squared is almost the same as R plus little r all squared. Because little r is so tiny, if we add it to big R and we square it, we're not going to get a number that's significantly different. And so it's approximately Gm over uppercase R squared. But hey, that's simply the gravitational field strength of Earth. Look at that's a constant value. G is constant, capital M is constant, uppercase R is constant. This value is constant, it's 9.81. So what do we assume here? We assume that the mass is not significantly larger or comparable to the size of the Earth, the mass of the Earth, and its distance must be much less than the Earth's radius. If we do that, then the mathematics allows us to have this value of G constant, 9.81 newtons per kg. Get used to using newtons per kg as the unit of measurement for field strength. There's nothing wrong with meters per square second since they are equivalent, but it's good to be interchanging between the units so you get used to the units of measurement. Okay, so now we have to move on to, we're actually going to kill two birds with one stone. We're going to talk about gravitational potential and gravitational potential energy. So gravitational potential and gravitational potential energy. Now, potential energy might be familiar to you, but potential maybe not so much. Potential difference, yes, but potential might be the first time that you're learning what gravitational potential is. So we know that gravitational potential energy, we'll give it the symbol EP, is the work done. So the gravitational potential energy stored in a system is the work done by one object on another to place that system into its current state. It is energy with respect to position. And if I do some very simple mathematics, I know work is force times distance. But wait a minute. For gravity, this will be Newton's law, gmm over r squared, times r. If you need to remember a simple way of getting this equation, so that's gmm over r. So the work done is gmm over r. So the gravitational potential energy is g uppercase m lowercase m over r. But the confusing thing is there's a minus sign here. We'll talk about why this minus sign arises. And the unit of measurement, I'll use square brackets to represent unit of measurement. The unit of measurement of potential energy is joule. Now, why is it that there's a minus sign? Where does the minus sign come from? Well, what do we know about objects that are very far from each other? Well, if the sun and the earth were at opposite ends of the universe, there wouldn't be any gravitational potential energy stored in that system because there wouldn't be an attraction. The attraction would be too weak to measure. So at infinity, there isn't any gravitational potential energy. It's zero. So let's take two masses, uppercase m and lowercase m, separated by a distance r1. The potential energy, remember, potential energy must be between a system of objects, not just for a single object. There must be multiple objects for an energy to be relevant. Let's take the same two objects, uppercase m and lowercase m, and reduce the distance between them. They're now separated by a distance r2. They now hold a potential energy EP2. Okay, so we're going to see why this equation has a minus sign. Now what I know is that R2, as I get closer, as the masses approach each other, when R2 is less than R1, then the gravitational potential energy of the second system is less than the gravitational potential energy of the first system. So how can I think of that? Well, think of that in this way. Here's my mass little m. As it moves towards the mass big M, let's assume we convert all of this mass. It starts moving from rest, moving towards the bigger mass. As it moves towards M, it gains kinetic energy in the absence of any other forces. The further it is from the larger mass, the greater its kinetic energy will be when it reaches the greater mass, since it will be accelerating for a much longer time. But the closer it is, like in the second scenario, the kinetic energy it gains is less, which can only mean that it has less potential energy in the second scenario, in the second situation. So wait a minute. What do I have? I have the potential energy decreases as the distance, the separation between objects in that system, r, decreases. So EP gets lower as we come from infinity towards zero. But wait a minute, we said that the potential energy at infinity is zero. So we start at zero at infinity and we get less. The only way that we can get less than zero is that if the potential energy is negative. Since it's decreasing from zero, it must be less than zero. And this is why the gravitational potential energy is negative, specifically minus gmm over r. That's the potential energy stored between two masses at any distance less than infinity. And where does this lead us to? Well, this leads us to potential. The gravitational potential which we give the symbol phi, or phi, as it's probably properly pronounced. So phi, the gravitational potential, is defined as the work done per unit mass in bringing a small test mass from infinity to that point in the field. So it is a function of r. It depends, like the potential energy does, on the position r, the separation between the objects. Similarly, potential also depends on the position in space. So it's 1 over the mass multiplied by the equation for work done is the same as the equation for potential energy stored in the system. That's minus g big M little m over r. And guess what? We get this to be minus gm over r. It only depends on the mass of the object causing the field. So at some point in space P, there doesn't need to be an object there, the field strength at a distance r is minus gm over r. Also negative because the potential, like the potential energy, decreases from infinity, and at infinity it's 0. And so let's write this down if I haven't made this clear enough. This is the gravitational potential. This is a new quantity that you are learning. Not the potential energy, but the potential. Remember, these two are different quantities. And the unit of measurement for phi, as we can see, is work done per unit mass. So that's joule per kg. We don't have a derived unit for gravitational potential. We use joule per kg. And so we've learned quite a few new concepts, quite a few new quantities at least. So to summarize everything, in an attempt to try and make everything tied together, let's summarize these new quantities. Let's take two masses, again, like we've been doing all this time, uppercase m and lowercase m, separated by a distance r, rather. For two objects, remember, a force can only exist between two objects, and so too can an energy. So the force of attraction between them is g big M little m over r squared. And the potential energy stored between these two objects minus g big M little m over r. Notice that the force decreases as 1 over r squared with the distance, and the potential energy decreases as an hyperbola, so a little bit more gradually than the force does, but still decreases with distance. So these two quantities will require two masses. That's why we have the product of two masses in the equation. But let's just consider a single mass, m, and consider a circle with a radius r around this mass. Then if I place a point P anywhere on the circle, and I say the distance in the point P is r, which means the radius of this circular orbit is r, then I can define the quantity of the gravitational field strength, which doesn't require a second mass, to be gm over r squared. And I can describe another quantity, the gravitational potential phi, as minus gm over r. No second mass is required. That gravitational field exists whether or not a force is there, a mass is there rather, to experience the force. So for two objects, we have the force and the potential energy. For a single object in space, there is a gravitational field with a field strength and a gravitational potential. Anywhere along this dotted line, the gravitational potential is constant, and so too is the field strength. So this was very brief, but again, this was just a crash course on the topic of gravitational fields to make sure you understand all the basic concepts that you need to know when going into a test or exam. On your end, a lot more reading is required. A lot more problem solving is required as well. So until next time, I'm Mr. K. I'll see you soon on Everything is Relative.